Hello everyone, I am Abdulrahman and today I am presenting our work, Transferable Neural 1TE for Changing Topologies. This work is jointly done by researchers from Purdue University and Meta. Traffic engineering pipeline takes as inputs a set of traffic matrices, a set of capacities, and a set of predefined tunnels. Then those are fed to a centralized SDN controller. Common examples are EBB controller, SWAN, and V4. This centralized controller has a global view of the network. It optimizes a network-wide objective, something like minimize link utilization, where it employs linear programming to route the traffic. Using LP solvers in the centralized controller has two main drawbacks. The first one is that input traffic matrices do not fully capture actual traffic matrix due to prediction error, and LP solvers cannot cope with the prediction inaccuracies, eventually resulting in suboptimal routing. The second problem is that LP solvers do not scale to large topologies. So recently, the community has shifted towards using neural models for routing. For example, last year we saw DOT and TEAL. Neural models can compensate for prediction errors, yielding better routing. As well as they are also faster and can scale to large topologies. However, there are some challenges that neural models need to address. For instance, networks evolve continuously due to multiple reasons, including organic growth, planned maintenance, or unplanned failures. The figure on the right illustrates the variation in the number of links over time in a real Cloud WAN network. It is evident that link failures and additions happen frequently. However, existing neural TE models focus on fixed topologies and fixed set of tunnels. Thus, they do not generalize to topologies outside the training set. For this, we propose HARP, which is the first neural TE scheme that can handle changing topologies. HARP is by design transferable across topologies. It preserves key invariances to natural input transformations like reordering of tunnels. HARP's neural architecture is aligned to the optimization model. In terms of results, HARP outperforms classical LP solvers. That is, depending on the traffic matrix predictor, HARP generates 5 to 13% lower maximum link utilization, MLU, on average. It also can be 100 times faster on large topologies. HARP performs well even with topologies or failures outside training data, while generating close to optimal MLU in all cases. On average, it results in 34% lower MLU than state-of-the-art neural TE models like DOT and TEAL. To motivate the design of HARP and explain where existing neural models fall short, let's consider why explicitly modeling topology is important. And to answer this, let's examine DOT. DOT is basically a fully connected neural network that does not model capacities, tunnels, or topology. To be concrete, it takes a fixed size traffic matrices as input and generate routing on fixed set of tunnels. However, when tunnels or capacities change, routing generated by DOT does not change. On the topology to the right, the upper tunnel should carry more traffic, since C1 is greater than C2. However, DOT is not able to distinguish these two scenarios, despite the changes in tunnels and capacities. To be precise, for the same input traffic matrices, DOT generates the same routing, regardless of tunnels and capacities used. Another issue to consider is why preserving invariances is important. If we look at these two topologies, we find them identical, except that the tunnels are relabeled. This relabeling has no effect on the routing. However, existing neural models like DOT and TEAL do not guarantee identical routing in the two scenarios. Please refer to our paper to know why. Preserving invariances is a prerequisite to generalize to topologies unseen in training. While designing HARP, we had two principles in mind. The first one is to ensure invariances to input transformations like node relabeling, tunnel relabeling, and traffic matrix transpose. The second one is to align its neural architecture to the optimization model. And by this, we mean introduce some components to HARP's neural architecture that mimic the iterative nature of the optimization algorithms. This serves as an example of the power of neural algorithmic reasoning. These two principles allow HARP to generalize to topologies beyond the training. HARP consists of four modules. The first one models topology and capacities, while the second module is responsible for modeling tunnels. The third one generates initial routing, and the fourth and final module is responsible for iteratively improving the routing. To be concrete, HARP takes as inputs the topology and capacities and feed them to a set of graph neural networks, which will generate a set of edge embeddings. Those edge embeddings will be fed to a set transformer. Also, tunnels described as sets of edges will be fed to the set transformer. Here I highlight that modeling tunnels as sets of edges introduces an invariance to the traffic matrix transpose. The set transformer is responsible for generating tunnel embeddings. Initial routing predictor will take it from here by feeding the tunnel embeddings and input traffic matrices to a multi-layer perceptron, which will in turn generate initial routing. The current routing will be used to evaluate network-wide MLU and highest link utilization in every tunnel. These two values will be fed alongside input traffic matrices and tunnel embeddings to a recurrent adjustment unit that is applied k times in order to iteratively improve the routing before generating the final one. We conducted experiments using 4 datasets. AllenNet is a data collected from a real cloud WAN. Giant and Abilene are public datasets, while KDL is a public topology with which we use synthetic traffic matrices. HARP was compared to 3 baselines: DOT, TEAL, and Gurubi, which is a widely used LP solver. We note that schemes were evaluated using a ground truth matrix, unless otherwise mentioned. But before we delve into the results and evaluation, it is essential to provide more details and characteristics of the ANONet dataset. ANONet is collected over a 4-week period at 1-minute interval, where every snapshot has a topology and a traffic matrix. We partitioned the dataset into 78 clusters. Within a cluster, tunnels are fixed. However, link capacities change in the form of partial and full link failures. For example, one of the clusters witnessed 250 unique link capacity configurations. However, across the clusters, also tunnel changes due to node or link addition. We noticed that 20% of the last cluster's tunnels are not present in the first cluster. We draw your attention that past work has only evaluated on static topologies. To evaluate the ability of HARP to perform well in such dynamic conditions, we trained it on the first 3 clusters, validated it on the next 3 clusters, and then tested it on the remaining 72 clusters. And to explain our metric, by normalized MLU, we mean generated MLU divided by the optimal MLU. And the optimal is generated by a clairvoyant LP, and it's only needed for plotting. As we see, HARP is within 20% of optimality 98% of the time, despite significant tunnel and topology changes outside training set. We then compare HARP to DOT, where we train and test on the same cluster. As we see, HARP generates significantly lower MLU. On average, HARP's MLU is 3 times lower than that of DOT. And this is mainly because DOT assumes static link capacities, and it lacks any mechanism to handle partial and full link failures. Working with DOT across the clusters will be even more challenging. After that, we examine the ability of HARP to compensate for prediction errors. We compare HARP to Gurubi on the predicted matrix. We see that HARP outperforms Gurubi by 9% on the 18th percentile when the predicted matrix is used. Benefits are even higher with other predictors. Please refer to our paper. We hypothesize that HARP learns to be robust to prediction errors. We then demonstrate one of HARP's invariances to input transformations. In this experiment, HARP, DOT, and TEAL were trained on a given set of tunnels. Then 2 experiments were conducted in testing mode. In the first experiment, we used the same tunnels in the same order. And as we see, all models perform well. In the second experiment, we used the same training tunnels, but in different order. Ideally, this reordering should not make a difference. However, only HARP retains its performance, while DOT and TEAL generate 1.5 times higher MLU. Finally, we compare HARP to another version without the recurrent unit to showcase the importance of aligning the architecture to the optimization algorithm. We see that on average, HARP's MLU is 1.6 times lower than that of HARP without a recurrent unit. Please refer to our paper to see more experiments, where we showcased HARP's ability to handle topologies outside the training set. We conducted experiments with full failures and partial failures. Also, we presented computation times. To wrap up my talk, we presented HARP, which is the first neural TE scheme that can handle changing topologies. HARP is by design transferable across topologies. It preserves key invariances to natural input transformations like reordering of tunnels. Its neural architecture is aligned to the optimization model. HARP outperforms classical LP solvers, as well as state-of-the-art neural TE models like DOT and TEAL. We made HARP's source code public. This marks the end of my talk. Thanks for your listening.